Cities are becoming hotter due to rapid urbanization. This phenomenon, known as urban heat island effect, occurs when buildings, roads, and other urban surfaces absorb and retain more heat than natural landscape. In this study, we use ArcGIS and remote sensing to analyze the spatial distribution of urban heat island in the city and examine its relationship with different land cover types. This finding can support better urban planning and sustainable heat mitigation strategies. Rapid urban development has significantly changed natural landscape, replacing vegetation, buildings, roads, and other impervious surface. This land cover change have altered the urban thermal environment, leading to an increase in land surface temperature and the formation of urban heat islands. Recent studies have shown that land cover plays an important role in influencing UHI intensity. Built-out areas generally experience higher temperature, while vegetation and water bodies help reduce surface heat. Therefore, integrating remote sensing with GIS provides an effective approach to analyze the spatial relationship between land cover and urban heat island intensity, supporting more sustainable urban planning.
Urban heat island is becoming a growing concern in many cities around the world. Several issues and challenges arise as urban areas continue to expand and temperatures continue to increase. As urban areas continue to expand, natural landscapes are replaced by buildings, roads, and other infrastructure. These materials absorb and retain heat, creating the urban heat island effect, where cities become significantly hotter than surrounding rural areas. Another major challenge is the lack of green spaces. The loss of trees and vegetation reduce the natural cooling through shade and evapotranspiration. Without enough greenery, urban temperatures continue to rise, making cities less comfortable and more vulnerable to extreme heat. The impact of urban heat extends beyond the environment. It also affects human health. Prolonged exposure to high temperatures increase the risk of heat exhaustion, heat stroke, and dehydration, especially among children, the elderly, and outdoor workers who are most vulnerable to extreme heat. Another challenge caused by UHI is the increase in energy demand. Higher temperatures in cities force residents and businesses to use more air conditioning for cooling purposes. High energy consumption increases the demand for electricity production, causing power plants to burn more fossil fuels and release higher amounts of greenhouse
So now, I will present a case study on urban heat island mitigation using remote sensing and geographic information system in Singapore. Urban heat island or UHI occur when urban areas become hotter than surrounding areas because of dense building, roads, and limited vegetation. As a highly urbanized tropical city, Singapore experienced this issue due to rapid development. To investigate this problem, the researcher collected temperature data from 18 weather stations along with spatial data on green marked buildings, national park, gardens, green rooftop, and major roads. Using ArcGIS, they applied GIS techniques such as buffer analysis, raster analysis, and inverse distance weight (IDW) interpolation to produce heat maps showing temperature distribution across Singapore. The results show that Marina Barrage and Newton had the lowest temperature increase, around 1.6%, because this area has a high concentration of green space and green marked building. In contrast, Tengah and Sembawang recorded the highest temperature increase, about 2.2%, due to limited greenery and fewer sustainable buildings. This case study demonstrates that remote sensing and GIS are powerful tools for analyzing urban temperature patterns and identifying heat-prone areas. The findings suggest that increasing parks, rooftop garden, vertical greenery, and green marked building can effectively reduce the urban heat island effect and support more sustainable urban planning.
Our second case study was conducted in Bengaluru, India, one of the fastest growing metropolitan cities in the country. Over the past 5 decades, rapid urbanization has transformed natural landscapes into densely built up areas, making Bengaluru an ideal locations to investigate the urban heat island effect. To understand this phenomenon, the researchers integrated remote sensing data from Landsat 8 and Sentinel-2 with Geography Information System or GIS. Landsat 8 was used to estimate land surface temperature, while Sentinel-2 provided detailed land cover information, including vegetation, built-up areas, water bodies, and bare soil. These datasets were analyzed spatially to identify urban heat island hotspots and examine the relationship between land cover and surface temperature. The analysis revealed that densely built-up areas and bare soil recorded the highest and land surface temperatures. In contrast, vegetation and water bodies consistently acted as natural cooling elements. Statistical analysis also confirms that built-up areas were positively correlated with land surface temperature, while vegetation and water bodies show a negative correlations, highlighting their important role in reducing urban heat island intensity. Based on this finding, the researchers recommended increasing urban green space, restoring lakes, developing mini forests, and maintaining at least 30% vegetation cover within development plot. This case study demonstrated that GIS and remote sensing are powerful tools for monitoring urban heat island intensity and providing scientific evidence to support sustainable urban planning and effective heat mitigation strategies.
25 years of satellite data has exposed a disturbing reality in Penang. This is the story of how remote sensing and geospatial systems act as the eyes and brains, revealing Penang's accelerating urban heat island effect. To investigate these changes, researchers first turned to remote sensing, assessing decades of data through the Google Earth engine. They specifically utilized images from Landsat 5 and 8, choosing data from April to minimize seasonal differences in temperature estimates. The sensor captured the Earth in thermal bands, recording radiation that is invisible to the human eye. But these digital images are just the beginning. They must be translated into a map of heat. In the digital laboratory, they convert these raw digital numbers into spectral radiance and then into top of atmosphere brightness temperature by calculating land surface emissivity through the normalized difference vegetation index. And they finally derive the land surface temperature. This process reveals a shocking reality, which is average surface temperature in Penang have increased by 8 degrees Celsius since 1996. To understand why the island is heating up, researchers use land use and land cover analysis to map the physical transformation of the terrain and classify the island surface into 4 distinct categories: urban areas, agriculture, water bodies, and forests. This geospatial method allows them to see that while the built-up area has expanded by 22%, the protective forest cover has dropped by 17%. These separate maps of heat and land cover are then brought together using Geographic Information System (GIS). Within ArcGIS, they perform overlay analysis by stacking their LST maps onto LULC maps. This integration allows them to calculate the urban heat island intensity by comparing the high temperature of the city center to the cooler surrounding rural areas. Their statistical models show a strong positive correlation between carbon emission and heat island intensity. Without the cooling effect of the forest, the sun's rays are absorbed by concrete and asphalt, raising the UHI intensity by 38% over the study period. Statistical evidence proved that carbon emissions are primary driver of this rising heat. However, the study provided a solution, which is to restore the balance. Penang must embrace reforestation and urban greening, such as rooftop garden, to reclaim its green shield and secure a cooler future.
The analysis of urban heat island intensity through ArcGIS and remote sensing provides a better understanding of how different land cover types affect urban temperature distribution. The application of GIS and remote sensing is an effective tool for assessing urban heat patterns and assisting in sustainable city planning. Understanding the connection between land cover and UHI intensity allows suitable solutions to be developed, including increasing vegetation coverage and promoting green infrastructure. These efforts are essential in reducing heat-related impacts and creating more sustainable and climate-resilient urban areas. Remember, the heat we feel today is a reflection of the choices we make in shaping our cities. Through technology and better planning, we have the power to transform urban spaces into places where people and nature can thrive together.